Hi community! Today we code vision transformers. In my last videos I showed you how to do an image classification. I showed you where the self-attention in vision transformer is and the status about cancer screening in 2023. Independent if you have a sentence transformer or a vision transformer, the transformer architecture is almost identical. So this means we have a pre-training model and then we fine-tune this model for a specific task. And today I show you how to fine-tune vision transformer on image classification. You could do it in an industrial application or for a biological. We take now the idea, we have a drone that takes pictures, and we have now to identify the type and the degree of the infestation and to fine-tune a vision transformer for this task. And as I know you want to follow along in a notebook, I have chosen here a very particular implementation from HuggingFace from Nate Raw, and it is called Fine-Tune Vision Transformers for Image Classification with HuggingFace Transformers. And here you have your Colab notebook. I'll leave you the link in the description of this video. I just adapted the notebook a little bit. So here we go. You know what a vision transformer is and that it has an encoder stack. We went through this already. So what we do, we say pip install our datasets from HuggingFace and the transformers from HuggingFace, and then load the dataset that we will use for fine-tuning our pre-trained vision transformers. So this means we need now a label dataset for our supervised learning. And there we have now, if you go here to HuggingFace, a specific dataset. It's called beans. So easy. We have three parts here. We have here a string, and this string describes here a specific file path we do not need. Then we have here an image. This is an important part. And we have a label, a class label describing the condition of this image for image classification. And we have the labels 0, 1, and 2. 2 means healthy, and the other one indicate some past manifestation. If you want to have more information on this, we have here the data fields and everything. And notice that the data set is already split in a training data set with 1000 images, a validation data set with about 100, and a test data set also with about 100 images. Beautiful. So here we go. Now we load this beans dataset, and then we have our images and our label describing the images in 3 classification tasks. So yeah, we have a look at the keys that you can see it. Data is downloading. Beautiful. And I want to show you the type that we are working here, because when we're working with tensors, you have to be careful to transfer your dictionaries to tensors. But at first, here our keys are very clearly in our dictionary now that we have the training data set, the validation, and the test data set. And if you look here, this is exactly the number of pictures and the number of images that I just showed you. So beautiful. And then we can have a look at the format. Yes, of course. But the interesting thing here is we use here the Python imaging library for the Python interpreter with some image editing capabilities. So we use the PIL format. Beautiful. Let's have a look at one of those pictures. So here we go. This is here a typical picture that we're going to analyze. And you know that here this is not a healthy plant, but we will have one of the first 2 labels. Now you can try to augment it with some luminance channel or whatsoever, but this is not the point in this video. I'll show you in a later video, but I would like to show you what we can do now with the classification. So at first we have here healthy. This has the index 2. We have then the angular leaf spot. I think this is the index 1. And the bean rust, the really heavy pest infestation, is, I think, 0. So this is it. Let's print it out. And we know that this picture here, this brown spot here on the leaf, is classified as angular leaf spot. Infected with angular leaf spot, a serious disease in bean plants. Beautiful. Now you can say, show me more examples. So this is just that you have a 3x3 image visualization where you have the classes now in each row. There's nothing to this code. You have it in the link in the description of this video. And it is just to show you, angular leaf spot has irregular brown patches. The bean rust has circular brown spots surrounded by white, yellow ring structures. And healthy, well, healthy just looks healthy, a green leaf as you would expect. So here we are. The first row, you have angular leaf spot, so this dark patches on our leaf. The bean rust, this is the real serious part with here the little white spots around. And then examples, 3 examples of a healthy leaf. Beautiful. So now we have to prepare our images for our vision transformer. And we have some beautiful thing here. And yes, I know. We have a feature extractor. What a feature extractor does is just prepares the pictures for you. Okay, yes, use the wrong transformation on your image and the model won't be able to understand what it's seeing. Yes, so more or less it is a normalization. So now to normalize our images for our vision transformer model, you have some parameters. You have here the sequence of means for each channel you can determine to be used when you normalize your image, the sequence of the standard deviation for your RGB, red, green, and blue channel. You can say here a Boolean operator if you want to normalize it, yes or not. You can choose here with a Boolean operator to resize the image, and if you choose yes, you have here the size. Normally default is 224 pixels times 224 pixels. So beautiful. So here we go. And now, of course, we have here our vision transformer feature extractor from a specific pre-trained model. And our pre-trained model, no wonder, is what we used in the last 2 videos from Google, the vision transformer base model with a patch 16x16, image size 224x224, with millions of pixels of images. Sorry. So, and if you are not sure, here we go, HuggingFace. You go here, Google, Vision Transformer Base Patch 16.224, and you see here in the description, this is the pre-trained model on the ImageNet, which has 14 million images, has 21,843 different classes, and the images at a resolution of 224x224. Exactly what we need, only a pre-trained model. This is it, and we fine-tune it now on our specific dataset. So here we go. Yeah, this feature extractor, if you think this is something miraculous, it is rather easy. It just tells you, yes, I did normalize, I did rescale, yes, this is it. The width is 224 times 224 pixel. Beautiful. Nothing else. Now, if you want, of course, here you have to go from the image pixels now to a tensor, and nothing easier than this. You put in your image, you say your return tensor, please a PyTorch tensor, and your pixel values is now a tensor for each 3 channels. Remember, we have an RGB, red, green, and blue channel. So for each of the 3 channels, we have here the pixel values normalized. So we do not have, I don't know, 115,000.2 and minus 6,800,000, but we have normalized pixel values. Beautiful. Okay, now that we know how to read in the images and transform them, let's write a function that will put those 2 things together to process a single example. So what we do, we have our feature extractor, which will return the pixel values as a PyTorch tensor. And we want to have attached our labels. Remember the 3 classes, healthy, rust, and this pattern, 0, 1, and 3. Let's do this. We define here this process example function. And if we apply it here, for example, here on a single picture, You have here your pixel values. This is the tensor for RGB. And then you have now attached a specific label describing the condition of the leaf in these images. This is it. Great. Next point. Yeah, there's in pandas, if you remember, we had a panda data frame, and then we used here the transform command, by example, to find the square root and the result of Euler's number raised to each element of the data frame. And we just used here the panda data frame dot transform and the function that you want to have. And now, more or less, we do in BERT, we can do the same. And now, if we want to augment our data set, we will use something similar. We will use here the HuggingFace dataset.map command in batch modes. And this will let you control the size of the generated dataset freely. It is nothing in particular. It is just what I just showed you. It is just here the most efficient way to encode it. So we have here our transform function for the batch. So we take a list of images and turn them into the pixel values with our feature extractor I just showed you, and we get a PyTorch tensor back. And we include the label, and we do this then. We have defined this function. Yes, yes, yes. And now we already have it in cache. Beautiful. We can now directly apply this to our whole data set using the command dataset with transform. And we do this, and now everything is now transformed. Yeah, I know. I'm coming to the training part. Yeah, and if we want to have a look at this very easily, what we achieved, we have here the pixel value, the tensor values, and you're not going to believe it. Here is our label attached to it, and now it is done for the complete training dataset on what we will fine-tune our vision transformers. Finally, training. So what we need for the training pipeline, we have to define a collate function. I show you we have to define an evaluation metric. It will be accuracy. We have to load the pre-trained checkpoints. Yes. And finally, the training configuration with the learning rate, the hyperparameter, and everything we need to fine-tune now our pre-trained model. Now, collate function is exactly what we had last time. I don't have to repeat this. The evaluation metric, as I told you, is simply accuracy. You are familiar with this particular part. And then, of course, we need a pre-trained model. And as I told you, we will use this from Google, ViT base patch 16.224 with our, how many million pixels? 14 million images. Beautiful. So here we go. We have now the head for image classification. And this is now for the fine-tuning part. You remember, we have a model transformer with an image classification head on top. Exactly like we did with BERT, where we had then for the fine-tuning, you put a specific head on top of your BERT model. And here we do exactly the same. We take now our vision transformer model, and we put here a classification head on top. This is already predefined for us, of course, in HuggingFace. So all we have to do for constructing, for designing our model is we take here now in the fine-tuning task this additional header. We say we want to apply this to the pre-trained model. Pre-trained model is, of course, our big model here. And we want to have included the ID to label and the label to ID class. This is of course clear that we have a forward and backward compatibility. And we are ready to train. Now, there's a special command, but what we need now is for when we use the HuggingFace trainer, and we do not code it in pure PyTorch, but we're going to use this trainer, we have arguments. You know these arguments. Where's the output directory? What is the batch size? I tried to use 64, by the way, for our GPU. The number of training epochs, I set it to 8. You can choose here to go with half precision, but I say no, I want to go with floating point 32. What steps you save it, the learning rate you can define. If you want to push it to the HuggingFace hub, I say no, because I have just the demonstration. If you want to load the best model at the end, yes, and. And after defining everything, we are ready that we say, okay, let's build now the trainer to fine-tune our pre-trained vision transformer model. So we load from the transformer, from HuggingFace, our trainer. A trainer is simple, but a feature-complete training and evaluation loop for PyTorch, and it is optimized for HuggingFace transformers. And this is exactly what we use here. So this is the most simple way to build a training loop. So we say trainer. The model is our model we defined. The training arguments we just defined here. This is here. The data collator we defined. The compute matrix is accuracy. The training data set is prepared. The evaluation data set is prepared. And for our tokenizer, I showed you how we do this with our feature extractor. Beautiful. Yeah, maybe I should execute this. Oh, I didn't execute this too. Oh my goodness. I'm sorry, I forgot to execute everything. So now the trainer is here, and then we are now running trainer.train. This is the main command for the training. And as you can see here, oh gee, how long this will take, I have no idea. Number of epochs is 8. Batch size is 64. Oh yeah, let's see if our GPU RAM, would say at 80%, but I hope it will be stable. I hope we will not crash. But for the time being, for 8 epochs, it tells us about 5-6 minutes. I will be back with you in a second. And we are back, and you can see we are close finishing our 8 epoch. We have our 85 million free trainable parameters, 8 epochs, GPU RAM was stable, system RAM was stable, beautiful. You can see here our evaluation, our running evaluation has an accuracy of 99%, so really nice. Yes, 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 yes. Of course, if you do not want to use the HuggingFace trainer class, you can go with your native PyTorch. Remember this, for epochs in range of number, epochs is 8. For each batch, you have here the model with the batch defines the output. You have the loss, the backward propagation, you have your optimizer, your learning rate scheduler, everything as you know. But we use here the trainer functionality. And also, if we do not evaluate our newly fine-tuned vision transformer model, here are our validation data set and our test data set. And as you can see here, the evaluation accuracy is also 99%. Beautifully. So we set out to train, to fine-tune this on our pre-trained vision transformer model, and we achieved this. Now here you have in the notebook also, if you want to push this model with your name, with your credential to the HuggingFace hub for the community, this is the way to do it. You see, it's really easy. This is all that it takes, and you have published your model. This was it. You see, it is very easy to fine-tune it, but if you want to go a further step, I want to give you 2 literature insights. At first, please have a look at the GitHub from Google Research, the Vision Transformer. Here you have Vision Transformer and the mixer architecture. Here you have everything in a repository where they explain things beautifully. Of course, also as you see here with ImageNet 21K dataset, this is how we did it. Of course, here you have then for the TPU cluster in the cloud, you have here fine-tune a model. But as you can see here, we are operating then in JAX on the Google Cloud infrastructure. If you are interested, if you want to improve your training or your fine-tuning, there's a very interesting article, preprint from Archive from June 2022, so version 2, and they examined how the best way to train and fine-tune vision transformers. And they said they found if you prepare your visual data, your augmentation, your regularization of your data, you can get models with the same performance compared to models that are an order of magnitude more, have more training data. So the better you prepare your visual data, the more efficient your system, your vision transformer system will be. Well, of course, and just to give you a short preview here, for example, if you look here at this visualization, you can see here your vision transformer base and large, and you see here, normally if you have here the pre-training data size with 1 million, this is about, I don't know, let's take the blue one, the base model 32. You have here about 63%, let's say here 63%. And if you take the same pre-training data set, but you augment it in a beautiful way and you have a regularizer, then you can achieve suddenly, I don't know, 78%. So you go for 63 to 78% here if you're in your accuracy after the fine-tuning what we have just done. So the better you prepare the input data, the clearer are the pictures, the easier it is the model to achieve a higher accuracy. Well, this is exactly more or less what we expected. So here you have your further literature. I think it's really interesting. But otherwise, this concludes here our training, our fine-tuning a vision transformer on a pre-trained vision transformer. I hope you enjoyed it. This task is finished. You see GPU RAM, system RAM, everything stayed within the normal boundaries. So give it a try, experience yourself. Maybe you do not take here a data set of, I don't know, leaves. You can do it whatever you are interested in. Maybe it's cars, or maybe it's some technical content, maybe some helicopter, whatever you like. If you have a training data set available, a labeled data set, where you have an image and a particular description that characterizes this image, and you want to have a classification task, it is as easy as I showed you, almost the same as in the NLP BERT model. So give it a try with vision transformers. I hope you enjoyed it, and I see you in my next video.